Hi guys, welcome to Learn Electronics Repair. I caused quite a stir with a video a couple of days ago about a burnt out resistor, which is this resistor in the circuit here. So this is the circuit I reverse engineered from a faulty amplifier. The amplifier powers up, but there's no audio coming out, and I realised I had a bulged or blown capacitor, had a burnt resistor. I thought the opto isolator was faulty. Now it looks like it probably isn't, but we'll just have to really check that again. So let's look at this resistor, and the question of course was, what value is it? And we can see the markings: brown, black, green, then it's burnt and yellow, or yellow, green, black and brown. Okay, and according to the color code, if we start from here, this is 1, 0 and 5 zeros, which is a 1 mega ohm resistor. From this end, it's 4, 5 and no zeros, or a 45 ohm resistor. However, as I pointed out in the challenge video, none of these make sense, because we can see this circuit, which I described, a capacitive dropper, effectively charges this capacitor. And the capacitor is rated at 16 volts, and that voltage is powering the LED in the opto isolator. So the voltage here is going to be something less than 16. That's the absolute maximum it would be. It's probably going to be 12 or something like that. I suppose. I don't actually know. I did measure it later and found it wasn't, by the way. So this resistor, if this was a 45 ohm resistor, I calculated if this was the correct value, then the current through this LED in the opto isolator, current equals V over R. We'll assume the voltage was 12 divided by 45, and that equals 267 milliamps. So that is much too much for the LED. I actually looked at the data sheet, and the data sheet tells me that the maximum current there is 60 milliamps. So it's not a 45 ohm resistor. If we look from the other end, then we come to 1 mega ohm, and we can do the same calculation. So in that case, if this was 12 volts, then the voltage would be 12 volts divided by 1 million ohms. And I miscalculated this in the previous video and said it was 120 microamps. It's actually 12 microamps. And that, in fact, even 120 microamps is too low. Yeah, it's too low. So I then put a 1 meg resistor in here anyway, because it can't do any harm, basically. And I found I had about 28 volts across my 16 volt capacitor, and presumed the reason being that there was no load. This resistor was too high to pass any current through the LED. The voltage across the LED was about 0.85 of a volt, and when I switched this on and I measured across this transistor, it wasn't switching on. So we can say for certain it's not a 1 meg resistor. So the question is, what is it? Well, if we were to read from this end, 105, that would be the tolerance. Okay, and the tolerance band of yellow is not a valid tolerance band. That code does not exist in the resistor color code. It could be gold, which would be a 5% 1 meg resistor, but we know it's not a 1 meg resistor anyway. So we need to go the other way round. And this would say 4, 5 and no zeros, 45 ohms, but we know it's not that either. The last stripe is brown. Now that tells us, if that is the tolerance stripe, this is a 1% tolerance resistor, a very close tolerance. And if this is a 1% tolerance resistor, it must have a 5 band color code. So there must be another band on here. And where is it? Well, the only place it can be is in that burnt area. So from that, I figured out this must be a 5-band code. I must have 4 something 5, no zeros, 1%. And some people say that straight edge there is the edge of a band, black. Yeah, and from the other side, we see the same. Okay, so the value is 4 something 5 with no following zeros, 1%. I also measured from this end to the edge of the burnt bit, and I was seeing about 300 odd ohms, 300 to 400, and I surmised that the value of this resistor intact was somewhere between about 500 ohms and a kilo ohm, because that would give a sensible current through the LED. Okay, and putting that load on the capacitor in that circuit meant it wouldn't charge up to 28 volts anymore. But what is the mystery value? Well, the way I figured this out, my 4 AM moment, is that if this is a 1% resistor and I can see 2 of the digits, if I find the chart of all the possible values for a 1% resistor and find a code that is 4 something 5, and hopefully there's only one of them, that's the correct value, and therefore I know what colour this is. So I googled for 1% resistor values. Okay, standard resistor values, it brought this one up, and we can see all the possible values for 1% resistors, called EIA E96, but I didn't specifically know that correctly. So these values can have no zeros after them, they could have 1, 2 or more zeros, they could be divided by 10 or 100 depending on the multiplier stripe, everything from silver, gold up to, well, I guess into the mega ohms or 10 megs is green. Okay, and we want 4 something 5, and you can see all the possible values here, and only one of them, 47.5, can be correct. So the 3 coloured stripes are 4, 7, 5, and then it says decade multiples are available from 10 to 100. So 475 is the value of my resistor, ohms. So quite clearly that should be a violet band, 475 and no zeros. By the way, if you were confused, to get 47.5, this would be gold. Yeah, to get 0.475, it would be silver. So we know what it is, 475 and no zeros, 1%. We can now calculate then the current that would flow through the LED in the opto isolator. So again, R equals V over R. We'll assume 12 volts again, and we'll divide this by 475. Okay, well, it's about 1/10 of that, I would say, because that was divided by 45. So the current flowing through our LED is 25 milliamps. Also a nice round number-ish, if we can call 25 being odd, a round number, but hey, maybe you know what I mean. So 25 milliamps, the rating is up to 60, that's right in the middle pretty much. So that also makes sense, and that's the value of the resistor. To prove this then, I now need to fit the resistor of the correct value and then power this up and see whether the opto isolator switches the transistor or not. There's a couple of things we want to talk about here though, just before I do that. Firstly, what does this circuit do? I presumed it was some sort of brown out detector, so if the voltage on the input was too low, this wouldn't illuminate properly. This is a photo Darlington transistor, so it has a very high gain, and we can detect if the input voltage is below a certain level, and presumably disable the amplifier. As rightly pointed out by some of the people in the comments, and by the way, well done to all of you who got this right, Yeah, you guys are good. And for those of you who didn't, well done for taking the guess, and hopefully now you can see why you weren't correct. Okay, we all weren't. So what does a circuit do? Is it a brownout detector? You guys, or some of you, have persuaded me that it isn't. And the main reason for that is that this capacitor charges and discharges relatively slowly because there isn't much current being drawn from it. It's not being provided by that much current, and that would cause a delay in the LED going dimmer if there was less input voltage. So rapid brownouts, it wouldn't detect them, it wouldn't react fast enough to really say we have a low voltage condition. What is much more likely is this is a soft start. So because this capacitor has reactance, which is like resistance, it takes a finite amount of time for this capacitor to charge up, okay, to a brightness sufficient to light the LED to tell the circuit we now have power. So if this is connected to some sort of mute signal, for example, then this is probably designed to stop a thump on the speakers when you first switch on. It only activates the speaker or connects the speaker, probably via a relay, once the power is up and stable. So I would say I agree with those of you who say this is a soft start circuit. It makes more sense than my suggestion. Similar vein, detecting what's happening on the mains, but for a much more sensible reason. And in fact, the reason for this capacitor now makes much more sense when we consider this as a soft start. Okay, that's the first thing. Why did the resistor burn up? Well, the resistor burnt up because it passed too much current. Yeah, that's the only sensible answer. It passed too much current, therefore it burnt up. Considering there should be 25 milliamps flowing through this, and we know the value of the resistor, let's work out what the wattage is. So if we again assume this is 12 volts for now, this drops 1 volt. It's an infrared LED, so that means there's 11 volts across our resistor. Okay, we know the voltage across the resistor, 11, and we know the current in amps, 0.025. So that 11 times 0.025 is the wattage. And we can see without even using the calculator that if that was 10, this is going to be 0.25. Okay. And if it's 1 volt, well, it's that. So we're talking about 0.275 of a watt. And I think the resistor is a half watt. Can't see it being a quarter watt, it's too low anyway. So for that to burn out, it needs more current. And whatever caused the surge in current, where did the current flow? Well, it flew down here, through there, and back to here. So whatever current burnt that out must have passed through the LED as well. And that makes me suspect there's probably a problem with that LED that is still working, but as we experimented on the live stream, you can stick several 100 milliamps into an LED and it will still work, but if you push it too far, although it still works, it doesn't work at its proper brightness. So it may well be that that is also a kind of walking wounded. Okay, so what we're going to do is we're going to fit the resistor, 475 ohms. We're going to power this up again. We're going to measure the voltage across here. We'll see what's happening on the output of this opto-isolator, and I do have some of these, so I may change that as well, depending on the results. I don't have a full set of 1% resistors, so I don't have a 475 ohm resistor. What I've done is I've taken a 470 ohm, so this is like 470 and no more zeros. Yeah, you can see how the stripes work now. I've taken a 470 ohm, so our 41 would have had green there, 475 and no zeros. And I've connected, this is a 15 ohm resistor in series. Now, that's because the tolerances are all wrong on these resistors. They don't read correct. Yeah, I tried some lower value resistors and it didn't give me what I wanted. But with a little bit of experimentation, I have 470 to 473.5. So that's very close. Okay. I have another query about this circuit for you guys. What do you think? This resistor is setting the point at which the LED turns on. Okay. But so is this resistor, and so is this capacitor. So the value of this resistor, which is not a close tolerance resistor, and in particular the value of this capacitor, which is definitely not a close tolerance capacitor, will have an effect on the amount of time it takes this to charge. And this resistor, which is very close tolerance, will have an effect on the amount of time it takes to discharge. And between a factor of all three, will effectively set the time. But if this is a soft start, how critical can that be? Yeah, I mean, yeah. Do we really need that? Did they just have a whole bag full of these resistors so they stuck them in? I don't know, but I don't think it's quite as critical as the tolerance of that resistor suggests. I've mounted this upside down again on here just because there's mains voltage. I don't want it flapping around on the desk. So first thing, let's measure the voltage across this capacitor. So we'll switch it on. Okay, what do we have? Well, it's now 14.47, so that's fine. Across the LED, 1.23. Yeah, I mean, that's okay for an LED. They usually read about 1.05 on the meter, but it's got a little bit more current flowing through it, so that goes up. So that also looks okay. What's happening with the transistor? So I'll just measure across the transistor here in resistance mode. So that reads 4.6K. I'll switch this off. But yeah, up it goes into the mega ohms. Now you can see the delay with the capacitor charging and discharging, I guess. What voltage is in that capacitor now? Yeah, 0.8 of a volt, so it's almost discharged. Let's connect back to our opto isolator. Okay, so we see well into the mega ohms. Let's see how much delay we get now when we power this up. Okay, let's just try it. So, well, this was auto ranging, so it's probably a bit hard to see how fast it's doing that, okay? But we can see there is a delay, but it's a very short one. Okay. Once again, on. It's certainly reacting. So there's a very good chance that this will fix the problem on the amplifier. I'll try it on another video because this is not a repair video, and it helps people to find the videos for this because I actually made the first half on this amplifier, okay? But that connector there connects onto this board. Now, we have here, this is a tri-amped active speaker, so 3 speakers in one cabinet. This is the power supply. Yeah, this is the class D amplifier, which is the woofer. Okay, this is the connection to the woofer, in fact. This is the mid-range amplifier, which connects to the mid-range speaker, the medium-sized one, on these red and black wires. And then you can see down here an IC amplifier chip. This is the tweeter amplifier, which goes down the yellow and blue to here. So this connects to both the mid-range speaker and the tweeter, and this is the woofer. So that's where it goes. And this little PCB, which sends a signal from the opto isolator, plugs onto here. And this is effectively the board which splits the signal. So it takes the incoming audio and it splits it into the 3 bands for the speakers. So active crossover with 3 bands. And if this is going to mute the output until the power's on, this would probably be the board to do that. Yeah, so I also think that's another good indication that this is receiving the signal from that opto isolator and taking the mute off. Okay, I hope you enjoyed that, and I hope you followed the discussion of why many of you were right and why I'm convinced that I am right on this one. Everything seems to be okay now. So guys, again, Chat down there. Let me know if you enjoyed this contest, and I hope to see you all soon again on Learning Electronics Repair. Ciao for now.